Okay, so we have May 2019, paper 3. This is the A section, so it deals with data analysis type stuff. This might be concerning physics that you're already aware of. Frequently, it's physics that we haven't studied because it's not so much about the content or the concepts of the physics, but more about the data that they provide and how we manipulate it. They're data manipulation questions. And so here we have an Atwood machine with two masses, and it talks through how you can get the acceleration, or rather that the gravitational acceleration is given by the acceleration of the system times the sum of the masses divided by the difference between the masses. And so they give us values for acceleration, mass 1 and mass 2, with their values and their absolute uncertainties. And so A1 says calculate percentage error in the measured value of G. And so we break it down into its parts, remembering that for addition and subtraction, you add the absolute uncertainties of the values that are being added or subtracted, and for multiplication or division, we add the percentage uncertainties of the values in question. And of course, here's the formula. Says in the measured value of G, the formula for G is given right here, where it's the acceleration times the sum of the masses divided by the difference between the masses, and the values for A and M1 and M2 are all given right there. And so we start from the inside and work our way out. So both M1 and M2 have an absolute error of 0.001 kilograms. So when you add the two values, you wind up with an absolute error of 0.002 kilograms. When you add the two values of 0.125 and 0.120, you get 0.245 plus or minus 0.002 kilograms. 0.002 kilograms is 0.8163, etc. percent of 0.245. When you round the 0.816 off to one significant figure, we get 1% error in that as a percentage error in M1 plus M2. Now for M1 minus M2, they had the same absolute error of 0.002 kilograms. However, by subtracting the two values, we don't get 0.245, we get 0.005. That would still be plus or minus 0.002 kilograms, but that 0.002 kilograms is a much bigger portion of 0.005 than it is of 0.245. In fact, that's a much larger percent difference, percent error, I should say, of 40% as opposed to 1%, because 0.002 divided by 0.005 is 40%. Then, of course, by dividing M1 plus M2 by M1 minus M2, in dividing, we need to work with percentage error. And so we have the 1% for the M1 plus M2, but the 40% for M1 minus M2, and adding the two of them, we get 41% for that expression. Then we need to multiply times A. Now A has an absolute uncertainty of plus or minus 0.002 meters per second squared. And again, if you're wondering about the units, saying that meters per second squared are not compatible with kilograms, this is one of the reasons why we deal with percentages. Percentages don't have a unit. So then let's figure out the percentage difference on that 0.002 on 0.204 meters per second squared. And so the 0.002 meters per second squared is 1% of 0.204 meters per second squared. And I converted to percentage because I am multiplying A times the quotient of M1 plus M2 and M1 minus M2. And so we see that G is the product of A times that quotient of M1 and M2 and M1 minus M2. So we already figured out the M's as 41%, and A brings in an additional 1%, and so we add the percentage uncertainty, and so ta-da, the percentage uncertainty in the measured value of G is 42%. Note that this question has 3 points allotted to it, so let's pick out the 3 points according to the mark scheme. And interestingly, the first point actually is the majority of the work, is figuring out what is the percentage error in the masses and also in the acceleration. That's 1 point right there. Then they actually give you a point for adding 41 plus 1 equals 42, according to the mark scheme. I'm being facetious. Rather, they're giving a second point for acknowledging that percentage errors should be added when working with multiplication or division. That's actually what the second point is for. And then the last point, point number 3, is for getting the correct answer. Ding, ding, ding. All right, now let's go for II. It says deduce the value of G and get its absolute uncertainty. So let's go back to the equation for figuring out what G is. We have that the formula for G is given right there, so let's go. Running the numbers, we find that G is 9.996 meters per second squared. We control for significant figures. We actually find in the denominator, when you do m1 minus m2, you're only left with 0.005, which is one significant figure, and so our answer is going to be one significant figure in the second power of 10. So 9.996 will actually round to simply 10 meters per second squared, and then it says find the absolute uncertainty, and so we found in the I earlier that the percentage uncertainty is 42%. 42% of 10 is 4.2, but we need to, again, watch those significant figures. So 4.2 is not appropriate, and our final answer is, voila, G is 10 plus or minus 4 meters per second squared. An acceptable answer according to the mark scheme is 10.0 plus or minus 4.2 meters per second squared. The first point is for getting the correct value. The second point is for appropriately controlling for significant figures. And I purple boxed double I did not purple box single I, so there you go. The question continues on the following page. Oh, very good. Okay, so B, advantage and disadvantage. Using two masses that are almost equal, what would be an advantage? And with reference to the magnitude of the acceleration that is obtained. Let's revisit the experiment to see what they're talking about. So this is an Atwood machine. So we have two masses over a pulley, and it's saying there's an advantage in having M1 and M2 be almost equal. Well, if the two masses are very close in value, then let's put it this way. If they were equal in value, then there would be no acceleration. They would balance each other, and that's just fine. In fact, there are systems, they use that sometimes in restaurants, where they'll have a weight attached to a lamp, and the lamp and the weight are of the same mass, and so you can actually adjust the height of the lamp using the mass on the other side, and it's not going to whip the lamp over the pulley and crash into someone's dinner. There's no acceleration because the masses are equal. But if the masses are near equal, there's going to be acceleration, but not that high. So what advantage does that give you? That's the question. And so, like I said, the acceleration is a small value and the time of actual motion is large. So that is 1 point of 2, and to acknowledge that. But the second point is, well, like, what does that get you? Why is that good? And so if you have a large time and a small acceleration, then it's easier to measure for a human being actually measuring the experiment, or really for any apparatus measuring the time of the experiment with a larger time and a small acceleration, the more precise measurement can be made. I should probably say more accurate measurement could be made. And again, to be clear in terms of what they're asking for, there are 2 points here, because notice that it says state and explain. So the first point there is the statement, the second point is the explanation. Now, II says, what is the disadvantage with reference to answer to A double I? So it seems that based on my argument for I, that yes, you would want to keep the masses very close to each other. It gives you plenty of time to measure. Sounds hunky-dory. But if the masses are close to each other in value, there's going to be a large percent difference in M1 minus M2. Let's revisit. So notice in the M1 plus M2, that percent difference was 1%, NBD, correct. However, M1 minus M2, that percent difference was a whopping 40%. And it's 40% because the values of M1 and M2 are close to each other, And so the difference between M1 and M2 yields 0.005, but with an absolute error of 0.001 kilograms, when you add those together, you get 0.02 kilograms, and yada yada yada. We get 40% error on that measurement. So maybe if the masses were too close to each other, that does not actually serve our purposes. And that percentage difference carries through. We saw that earlier with our percent difference on G, that our M1 plus M2 was 1%, sweet, but M1 minus 2 was 40%, wah wah. And so when you throw them together, that 1% plus 40% gives us a percent difference in G of 42%. You can see that in the absolute error that G, based on this experiment, has a value of 10 plus or minus 4. Which is kind of broad. Ladies and gentlemen, is number 1. But don't be sad. There are more than that. Oh, hey, look at that. There's another one. Yay! Let's go. So in this question, it's actually a pretty interesting setup. They have a cylinder. There's no three-dimensional image. That's actually a cylinder of paper that a fixed load is placed upon. And then they put the same load on top of the cylinder, and then once they get high enough at a certain height, the cylinder collapses, and they note the height of that cylinder. Now keep in mind, this experiment is not comparing the diameter or height of the cylinder versus the load, because the load is fixed, that is held constant. And apparently there is a theory supporting this, saying that the height of the cylinder is equal to some constant times the 2/3 power of the diameter of the cylinder. And so the student, to linearize their data, plotted the third power of the height times 10 to the negative 4. That was probably just to make the y-axis, in the tens range, just for convenience. And then the square of the diameter is on the x-axis, and then that linearizes the data. And then the first question, A, says, why does the student's data supports the theoretical prediction? Well, let's take a look at the theoretical prediction. That is h equals c d to the 2/3. And again, in order to linearize, really that linear equation of the dependent variable is some constant times the independent variable. And we really kind of do have that form already. We have the h standing in for y as the dependent variable, and then we have some constant, which we could get from the graph. And then the thing is that we don't have just some straight up independent variable. We have d raised to the 2/3, so we have to deal with that 2/3. I suppose the student could have taken the diameter data and raised it to the 2/3 and plotted that on the x-axis, but they decided to plot d squared. Maybe it's just easier that way, but here's how that worked out. So the graph, as we can see over here, is h to the 3rd versus d raised to the 2nd, and here's why that is. In order to make d squared instead of d raised to the 2/3, they raised everything in the expression to the 3rd power to get rid of the 1/3 that d is raised to. So if I raise everything to the 3rd power, then that 3 goes away. So we get that h to the 3rd is equal to c to the 3rd times d squared, which is what the student had plotted. They're plotting h to the 3rd versus d squared, and it does fit that linear expression of y equals a constant times x. And so we can see that it does follow that relationship of a linear plot because the trend line is linear. All right, but that's not enough. Also notice that it passes through the origin. So linear and passing through the origin, means that the plot is directly proportional. Okay, that takes care of that. Just a reminder that when you're writing your answers, make sure that everything is within the box. I went outside of the box over here. I think if someone were grading it and saw the word direct proportion, I think they could figure it out. I think it's fine. But don't write answers like all over here or something, because that's not going to be scored. So again, the 2 points are figuring out where h to the 3rd is c to the third d squared comes from, starting with the original theory, and then the second point is for saying that the trend line is linear and directly proportional, which goes to the graph, the h to the 3 equals c to the third d squared. If it did not pass through the origin, there would need to be an extra coefficient with that. Now for B wants to know, find out what C is, and then also figure out the units for C. So again, realizing that this equation follows the equation of a line, y equals slope times x, the slope is going to be c to the third. So let's figure out our slope. We need to go back to the graph. Again, as a reminder, for IB, that when we're taking slopes, you need to pick points that are well spread apart. So I have 2 points here. Those are our values. And so y2 minus y1, that would be 60 minus 10. So there's our numerator. Now for our denominator. And according to my calculations, I'm getting 3.03 for my slope. The answer key, the mark scheme, says 3.0, only has 2 significant figures. Whatever, let's just go with that. I probably missed something somewhere, or my eyeballing that small graph is, I should be wearing my glasses, really. But anyway, so yeah, we get 3.03 for that slope, but that's c to the third power. We get a value for c of 1.4 when we take the third root of 3.03, and that agrees with the mark scheme. And then you're looking for units as well. So we can actually take that from the slope calculation. The slope calculation is the first point of 3, by the way. So this whole shebang right here is 0.1. The second point is the actual value of c, and then the third point are the units. And I can see the units are meters to the third divided by meters squared. And so meters to the third over meters squared gives a unit of meters for the slope. But remember, that's not the actual unit for c, because the slope is c to the third. So then when we take the cube root of c to the third to just make it c, we need to take the cube root of the units. And so the units for c are meters to the 1/3. Again, I rushed through the slope calculation units just as a reminder. When you are dividing exponents, you subtract the exponent. So meters to the third divided by meters squared, that would be 3 minus 2. That's where I'm getting the meters from for c to the third. And then the last question, C, says identify one factor that determines the value of c, that constant. This seems really complicated, but think about it. This is an experiment here, right? Let's go back to the experimental design. No. There it is. All right, so here's the experimental design, and it's like, okay, well, we have a cylinder of paper that you're putting a load on top of it, but it's not saying like what. Okay, so the load is fixed, but how much weight is that load, or what type of paper are you using? Not just type, but also the thickness of the paper. I mean, if you're using white paper, like white copy paper, there you can have white copy paper that's different thicknesses. So the thickness too. Could even be if you're rolling up the paper. How many times did you roll up the paper? Is it just one circle, or is there kind of like a little spiral effect going on in there? These are things you would need to think of if you were actually designing this as an experiment. But any one of those things, not all 4, any one of those things will satisfy that 1-point question. And that is it for May 2019, Paper 3, Time Zone 1, Section A, the data analysis question. Again, I just wanted to repeat, in the first part you had an Atwood machine, which is a common system that pops up in physics problems. But in the second part with the paper cylinders and the weight, that's not something that, you know, is commonly referred to. Actually, I think it's a pretty cool experiment, in my own opinion. But point is that it may be physics or an experiment that you've never seen before. Not only should you not freak out, but that is the point. It's not about the physics, it's about the analysis of the data and what's there. So yeah, there you go. All right, I'm not doing the other sections because for 2022-23, the plan is to do astrophysics, option D, but that's going to be handled separately. The intent of this video is only for the solution for the section A of paper 3. All right. Yep, there's 20 minutes. So thanks for listening, and I hope it was helpful.